Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show a basic example of forced convective heat transfer using SolidWorks flow simulation. Together with that, we will go for parametric study and finally flow optimization will be there. Let's see the model. It is consisting of a rectangular box which is made up of iron. At the left end, we will provide one fan and air will be forced from the left end to the right end, and the exit end we are having 4 slots, and in between one heat source will be provided. Let's say the heat source. This will be the heat source in between this inlet and exit end. At the bottom of this one we are having a plate. We'll be considering as a heat source which will be generating heat at a rate of 100 joules per second or 100 watt, and on the top it is having some fins of length 20 millimeter and breadth 20 and height will be 100 millimeter. Right, let's see the complete assembly. This is the complete assembly. So from left hand side we'll apply a fan and air will be forced to pass through these fins, and from the bottom of this one heat will be generating at a rate of 100 joules per second, and then finally these air particles will be moving through these exit ends. Right, this is about our activities. We'll apply different inlet conditions and also different dimensions to get a parametric study of different flow rates. By the same time, finally we'll go for flow optimization. We want to have a specific average temperature of the fluid that can be obtained with some optimization phenomenon. Okay, let's get started. The leads have already been provided at the inlet and the exit ends. But to start this flow simulation with an environment, and that environment will be created using Wizard. We're considering the project name as a default project 4 and considering the unit as SI system. Temperature we will consider as degrees Celsius. Next, it will be an external analysis and we'll consider heat conduction in solids. Next, gases, will consider air as the gas. And default solids, that means that fins will consider as aluminium. Next, default values will be taken for roughness. Next, thermodynamic parameters, that means the temperature of the walls etc. will be equal to normal temperature 20.05 degrees centigrade and pressure is equal to atmospheric pressure. Okay, and coordinate system is very important to see. Actually air will be flowing along the direction of x, so coordinate system should be x, reference axis will be x. Okay, let's finish this part. Now you can see that computational domain, it is very big volume or large volume. Our task should be to reduce this computational domain. As the domain volume is high, it will take more calculations time, so we can reduce it. Computational domain, edit definition, we can reduce this domain. Our computational domain is ready, so green check, and let's hide this domain. Next we have to apply these boundary conditions, that means fan to be provided at this end, heat source should be provided at the bottom of this one, and at the exit end it should be equal to atmospheric pressure. And another thing, that the wall material should be provided with a specific convective heat transfer coefficient. We're considering the wall to be made up of iron. First of all, we'll select that fan. Okay, you can bring it from tools, flow solution, insert fan. It will be external inlet fan. It will come from predefined axial fan. Here we can find different types of fans. We can select JMC products with higher diameter ranges. You can select the range of this one, like 90 to 25 12L. That means it will be having length equal to 90, breadth 90, and diameter will be 25 and 12 volt. We're selecting this one at the inlet only. So we have to select the inner side. So fan is selected at the inner side. Go and check. Next one, we have to provide the heat source at the bottom of this one, right? So better selection, we can do one thing. We can take a segmented view of the model and we can select the bottom surface perfectly. We can cut it with reference to top plane. We can cut it. Then we can apply heat source at this bottom end. So tools, insert, surface source, it will be providing heat at a rate of 100 joules per second. That means 100 watt. Now we can see the complete body. Heat source is provided. Next part, we have to apply boundary conditions. That means at the exit end, pressure should be equal to atmospheric pressure. So apply boundary conditions. It will be equal to environmental pressure at the exit ends. You can select all the exit ends together by control. Selected. Green check. Boundary conditions, insert boundary conditions. We have to select all the exit ends. You can select. So boundary conditions have been applied properly. Another thing is required, that is material should be selected for the boundary walls. Solid materials, insert. I've already selected aluminium for the heat source. We can define it again. Predefined metals, aluminium. We have to select that heat source. Done. Now another material is required for the walls. Insert solid material, predefined metals, iron. When you select that object, green check. So two metals have been defined, one for the heat source and another for the boundary. Now we want to see that the boundary also will have a convection from here to the air. So we can apply boundary conditions again. Insert boundary conditions at the walls. It is real wall It is having temperature equal to 20 degrees centigrade, 20.05 degrees centigrade, and it has a heat transfer coefficient equal to 60 watt per meter square degree Kelvin. To select that object, you can check done. So all the boundary conditions have been applied properly. Next one, we have to select some goals. Insert global goals. We want to have two specific goals. One will be average temperature of fluid, average temperature of solid, that is total temperature, and we want to have another condition, that means average wall temperature. Green check. We want to have another surface goals. Insert surface goals. We want to have average temperature of fluid at the surface, average velocity at the surface, and also average wall temperature at the surface. You can select any one specific surface. Suppose we select this bottom one. It's not selected. You have to select surface. Suppose you're selecting this one. Okay, done. Green check. So all the goals are defined properly. Next, we can run it. It has already started. You can see the solver window. Let the iterations move on. We can see the results from the solver window. Let's see it. These are all the goals. We can see separately, or we can see together also. Let's see. These are the different graphs. Better to see one by one. First of all, we want to see the temperature of fluid, average temperature of fluid. It started with 20.05 degrees centigrade, and after 244 numbers of iterations, the final temperature of fluid is 22.51 degrees centigrade. So temperature increase is not that much, from 20 to 22.5 degrees centigrade. Okay, this is average temperature of fluid. Now we'll see some other things like average total temperature, that means total temperature of solid also. It has started from 20.05 and after 244 numbers of iterations, it has come to 22.514. Okay. Again, you want to see wall temperature. Wall temperature is also 22.8391 degrees centigrade after 244 numbers of iterations, and also some surface goals. We can see that at the exit end, we're going to see temperature of fluid at the exit surface. Again, the same trend we can see that started from 20.05 degrees centigrade, and after 244 numbers of iterations, its temperature is 22.867 degrees centigrade. We can see the results right now. So from results, first result we see from cut plots. Insert cut plot. You can see from the mid of this plane, front plane, and want to view fluid temperature. Can check. See, so air is flowing from left end to right end. So at the beginning you can see at the left end the temperature of fluid is little bit less and the color is changing. The red color is temperature is very high. It is 42.59 degrees centigrade at the end. Initial temperature was very less, 20.03, and finally at the right hand side, exit end, not here the exit, at the end side you can see the temperature is 42.59 degrees centigrade. Okay, this is the cut plot along front plane. We can have the animation of this one, like cut plot, play. We can view this with respect to some other plane also. Let's clear and hide. Cut plot 1, edit definition. We want to see this with respect to some other plane. Maybe the plane will be right plane. We can drag it a little bit this side. Okay, green check. Let's view this one with respect to right plane. You can see the temperature at the top end is little high. So actually, as it is going up, the temperature of fluid is decreasing near the fins, because actually conduction is starting from the bottom only, and as it is going up, its temperature is decreasing, and at the airflow also, and because the convection, as air is flowing from the left hand side, its temperature is decreasing. You can see this one properly. Now see this flow in the form of an animation. Okay, let's clear and hide this part. Now want to see some other thing like surface plots also. Insert surface plot. Temperature of fluid, you want to see at the exit surface. Let's select all the exit surfaces. Temperature of fluid, you can see it is almost in the range of 20 to 24 degrees centigrade. At the top it is little less, and down it is. At the top we can see it is a mixed one. As we are moving down, the temperature is decreasing. Right. Next one, we want to see that flow trajectory. We want to see the flow trajectory from the inlet to the exit end. Okay. Okay, done. This part, let's clear and hide this surface plot. Let's view in isometric one. Now want to see the flow trajectories. Insert flow trajectory, and instead of 20 numbers we'll make it little more, maybe 50 numbers, and we want to see in the form of arrows only. and make this one equal to 0.005, and let's select the location from inlet. We want to see grain check. This is showing the flow trajectories. You can see the color also you can see properly. Particles from the fan, it is being driven from the fan and it is flowing through these fins, and at the exit end is passing through this parallel set of exit ends. Now we'll do one thing, we'll see this one in the form of an animation. So flow trajectories, clear and hide, and we'll see in the form of animation. Let's play it. We'll do one thing, we can have these numbers a little bit bigger, then it will be better for understanding. Let's clear and hide this part, and flow trajectories 1, edit definition. Instead of 50 we will make it maybe 100 numbers, and also the size will make it more. Nine. Okay. Now we'll simulate this one. Flow trajectories, clear and hide. Flow trajectories, let's play. It will be better to see this one from front view. Air particles are being driven by the fan and passing through these fins, and cooling is going on, and by the same time you can see that some air particles with red and yellow color, that means those particles are having high temperatures. Another thing is visible, that after collision with these fins, the color of the air particles is changing. The color of the air particles are changing. That means from dark blue it has come to lighter blue. That means its temperature is increasing a little bit. Initially it was 20.03 degrees centigrade. Now after passing through these fins, its temperature is increasing to in the range of 24.55 degrees centigrade. And again, some particles, while passing through these fins, temperature is in the range of 35 to 40 degrees centigrade. Okay. Now we'll do the main thing, to see the results, right? Let's clear and hide these flow trajectories. Now what to see the results? It will come from goal plots. Insert, want to see all the goals, show it. Now these are the values of goals. Like, it is better to see in the form of graphs, like history. It will show the temperature of fluid. Initially it was 19.85, or we can say the temperature of fluid initially it was 20 degrees centigrade, and after 244 numbers of iterations, its temperature is 22.35 degrees centigrade. It has increased a little bit because our heat source was generating heat at a rate of 100 joules per second. It was very less amount of heat it was generating. And the second one, we can see the total temperature, that is temperature of solid. It was also started from 20 degrees centigrade, and maximum it is equal to 22.5 degrees centigrade. And so world temperature, we can see it is 22.85 degrees centigrade, started from 20 degrees centigrade. Okay, these are the results. We can analyze these things results again all the other things, like one of the surface average world temperature is 22.85, and surface goal, the result is again temperature fluid at the exit surface is equal to average temperature at the exit end equal to, you can say, 22.85 degrees centigrade, right? These are the results. And velocity at the exit end equal to 0.4 meter per second. Okay, done. We got the set of goals. Now we want to go for our main concern, that is optimization. Goal optimization is needed, right? So for goal optimization, we have to start with solve new parametric study. We're going for new parametric study, and that parametric study will be based on different input variables. Initially, we started this analysis using specific value of our fins. Fin length was 20 and breadth was 20 millimeter and height was 100 millimeter. Now we're going for parametric study, and the parametric study will be based on different input variables. The variables may come from the initial conditions, or it may come from our dimensions. Here in this case, we are considering the fin dimensions as the input variables. So we have to take the dimensions of the fins. Okay, now we have to go for analysis. What type of parametric study we want? We want to have a specific type, design experiments and optimization, right? So for that, we have to depend on input variables. The input variables may come from these boundary conditions, or it may come from dimensions. We are considering that fin dimensions will be the input variables, right? So providing input dimensions of the fins. So for getting the input dimensions of the fins, we have to go to the initial drawing again. This is the initial drawing. We have to go to the drawing. You can see the dimensions. These dimensions is required, the dimensions of the fins we want, and breadth was also 20 millimeter, length, breadth both were 20 millimeter, height was 100 millimeter. We are not considering height. The cross-sectional area of fins will be acting as a input variable, right? Selected these things. Now the range of these things are required. We want to put the input variables in the range of 0.01 meter to 0.02 meter, and second one also same variables, same values we will provide, 0.01 meter to 0.02 meter. This range we are considering for these fins, and then we have to select the output parameters, and it is dependent on goals. We had a lot of goals, but here in this optimization, for reduction of time for calculations, we'll select only one parameter. Maybe we want average temperature of fluid. Okay, we're selecting only one goal. We can take a lot of others also, but we want only one for reduction of time for calculations. Okay, all these things can be taken. Okay, done. Next one, we have to select those scenarios. Different scenarios can be obtained. We can take number of experiments to 10. We can reduce it for minimizing time. Maybe we'll take numbers of experiments, only 5 set of experiments you want. Let's create it. Within the provided range of fin dimensions, we will get average temperature of fluid. Now we are taking 5 set of experiments, and let's see what will be the output with these different sets. These default values we can change as per our requirement, but we have taken the default values only. Okay, Let's run this. It will take some time for getting the results. Now out of all these 5 set of results, we can see which one is more important as per our requirement. Based on that requirement, we can go for optimization later on, right? Iterations already started. Mesh refining is going on. It will take some time. After getting the results, we start analyzing the results after getting it. So what we want, with a different set of dimensions of the fins, we'll get average temperature of feed. Okay, 5 set of experiments we have planned to get. We are waiting for the results for these 5 set of experiments. Okay, all the iterations have been finished and we can see the results right now. With the first set of results, we got our final temperature of fluid equal to 22.7. The second set providing the result of 22.59. The third one 22.43. Fourth one 22.93 degrees centigrade. And the final one is 22.82 degrees centigrade. So we are having different set of results. Now, as per our requirement, we can select any one of them, right? These are the only 5 set of results. If you want, you can have different set of results also. Maybe more detailed results we can expect with including all our required goals also. We have selected only one goal and a different set of results, right? We can see here that like temperature variation is very less. It is within a range of 0.1 to 0.2 degree variation in each of this. If we want to have a wide variation in temperatures, we can change the input variable as a heating surface, right? This is about our parametric study. Now we will move on to the last one, our goal optimization. In goal optimization, what we will do is we are planning to select one specific exit temperature, and we have to obtain that exit temperature with a specific fin dimension, right? Okay, so let's do it. We are starting optimization right now from solve new parametric study. It will be different types of optimization, so we are starting with goal optimization, right? Now the variables can be taken, different types of variables can be taken from these initial boundary conditions or can be taken from dimensions. We already told that we want the dimension of the fin to be considered as input variable, so we'll select the dimensions. Now for selecting the dimensions, we have to go back to the initial drawing. So we'll go back to the drawing again and see. This is the drawing, dimensions are there. Let's select any one dimension as taking the length of this fin equal to 20 millimeter. Again check, and we want to provide a specific range of this one. That means how it will be varying, the range of this variation we want. We're considering this variation from 0.01 meter to 0.03 meter. Within this range, we have to get one target value of average fluid temperature. Now that will be coming from criteria, and criteria is based on goals. We have a lot of goals, but we want to have only one specific goal. That means average temperature of fluid we want, right? You can check, and its target value we want in the range of 22.5 degrees centigrade, and we want deviation in the range of plus minus 0.1 degree centigrade. Okay, this is the targeted value, and within the specified range we want to optimize this. Okay, let's see the scenarios and run it. First of all, we'll try to optimize by considering the maximum value of the fin dimension. In the next step, it will take the minimum value. By this way, it will try to narrow the gap, and finally it will optimize the dimension of the fin. Okay, the iterations are going on. Let's move on. Whenever it is finished, we'll see the results. Okay, the solver window has finished all its calculations, so our solution is converged. We can see within 2 iterations we got the results. In the first design point, our targeted value was 22.5 degrees centigrade, and we got the value 22.328, and with a discrepancy of minus 0.178. And in the second one, we got the target value as 22.50, and it is exactly the same value what we targeted. So we got the optimum value of the fin dimension as 0.01 meter, that means 10 millimeter. So what we found, it can summarize the things what we did in our this optimization. We have taken some input variable as the fin dimensions, and based on the fin dimensions we got a targeted average fluid temperature as 22.5 degrees centigrade, right? This is all about today's forced convection through SolidWorks flow simulation. By the same time, we did parametric study and optimization. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.